All right. Hello, everyone. Welcome to episode 71 of the Warsaw Quantum Computing Group meetup. My name is Pavel, and I will be the moderator today. And we have pleasure to host our great speaker, Dr. Piotr Biskupski from IBM, and he will tell us what's new at IBM Quantum. So we'll check the latest tools, updates, and resources. Before we start, I would like to thank our strategic partners for supporting us as always. Sonovero R&D, Quantum.io, Onyx, Cogit, QLab, and ThinQubit, and of course our honorary partners for helping us in disseminating the information about the event. With this, I will stop sharing my screen and maybe just a few more announcements. So as you can see, this meeting is recorded, so the video will be later available on our YouTube channel, hopefully, if there are no technical or formal issues. Regarding questions, we've agreed with Piotr that this time there will be just a dedicated Q&A session at the end. So if you have any questions, you can post your questions here on the chat, and we can try to ask your questions at the end if there's time. And you also have the opportunity to just raise your hand during the Q&A and ask your question. So let's start. Piotr, thank you once again for accepting our invitation. It's great to have you with us, and we are looking forward to your presentation. So the Zoom is yours, and you can start sharing your screen.
Thank you, Pavel. Let's share my screen. And of course, the question, can you see it?
Yes, I can see your
Okay,
slides.
that's perfect. So, Pavel, again, thank you very much for invitation. It is a great pleasure to be part of the this great initiative, and hopefully we can do much more like in the previous years. So today I just want to show you something a little bit about the what's new in IBM, what are the new tools, what are the latest updates. I hope lots of you probably are using the IBM Quantum systems already because they are up and running since 2016, and you have the systems up and running in our IBM cloud and you can use them. So I will show you some kind of also how effectively and how strongly they are used by our community. So going back to the basics, of course, our mission as IBM is just bringing the useful quantum computers to the world. And our also one of our main goals is maintaining the industry largest fleet of utility scale quantum computers in the cloud for our clients, and of course for the community, because probably you know that all of the resources which are available in cloud, you can use it for free. So basically you have a couple of minutes which you can spend on the calculations and computations. And what is the most important part is not only the delivering just the quantum devices as a devices, but also the building, updating the innovation roadmap to build a quantum scalable computing system from hardware, software. Basically, what is our goal is going to the something which we called quantum advantage. I will tell a little bit more about this one later during this presentation. So one thing which is also important is development of Qiskit. Probably you are familiar with this system, with the software. And of course, open source it and give the user experience to all the people on the world to make quantum computing as easy as it is possible. So we are just giving some kind of learning stuff. We are giving the learning materials, and also we are just creating a new tools, which I want to show you also today. So some of the numbers, why we are interested with this one. So as you can notice that investment in the quantum computing is accelerating. So right now, those are the numbers for 2025. And as you notice, a lot of countries, a lot of initiative are around the building a quantum strategy and creating quantum technology plans. All the countries which I visit and which I have the contacts actually are building their own strategy, and also the European Union is building as well. So going back to the what we as an IBM can build and can bring to the community. So first of all, to run on quantum circuits in a very accurate manner and on the quantum hardware, first of all, we need the quantum hardware. So our systems right now consisting around 100 plus qubits, and they are available via our software. Second of all is the methods, how you can provide and execute quantum circuits on the hardware with a high accuracy. Another point is how to map interesting problem to quantum circuits. Computation tasks, of course, is something which we are interested, but the main goal is actually just building application for industry, for different industries, to build a system which will be capable to give them the advantage with the quantum system as a part of their computing data center. So a little bit about the roadmap. This is like a short roadmap. I would just want to show you where we are heading for the next 4 or 5 years. So first of all, in 2025, we actually we demonstrate the possibility to connect the quantum-centric data center with HPC. I will show you how it works. I will show you how you can deliver it to via Qiskit as well. So 2026 for us as a community, as a quantum community, it will be like a next year for reaching the quantum advantage. The quantum advantage for us is the main step to building and demonstrating the first error-corrected quantum computer, which, as you can notice here, we are planning to deliver on in 2029. So this is like a showing the path how to build the quantum system, which will be fully error-corrected. So what will happen after 2028? Actually, we are about to deliver first large-scale fault-tolerant quantum computer. This is our main goal for the next 4 or 5 years. How we want to achieve it? Of course, it will be not easy, as you can probably imagine, but I will show you a little bit about what we want to achieve it and what are the tools we will be using for this huge change. So probably you are familiar with IBM development and innovation roadmap, and right now we divided the roadmap a little bit differently. So we developed the roadmap where we are showing the development roadmap, where we are tracking the production of the hardware, software, and services. But also we add some kind of like another layer, which is the innovation roadmaps, where you can find the breakthroughs, some new releases, how some of the development milestones, which in some cases can be a proof of concept, but at the end of the day, they can evolve into the system directly into the, I would say, in Qiskit and also to the hardware. So I know this is like overloading for all of us. It's a lot of information, so that's why I just want to go a little bit to the details to show you a little bit easier to digest this very busy slide. So first of all, on the development roadmap, as you can notice, we have the quantum systems where we can apply algorithms to applications. Those advances will be let the adopters to run a specific for their own systems use cases. Next point is the discovering the new algorithms for a quantum advantage. I will show you how we will just create that again a little bit later during my talk. But as you can notice, first of all of those green buttons means that we already achieve it. So you can find those advanced classical transpilation tools, advanced classical mitigation tools already embedded into the Qiskit system. And another point will be the utility mapping for the tools. In some cases, we already have it, but to be for, let's say, 100% sure, we need to wait till the end of the next year, because we want to test it, we want to deliver it on the highest possible layer. One thing which we are focusing right now will be this part will be the orchestrating the workloads for the high performance computing and the quantum systems. This is what we want to achieve with some changes and some add-ons inside the Qiskit. So as you can notice, we are adding some special plugins inside the Qiskit, which can somehow be useful for connection and also the dividing the jobs into the smaller areas and then running those chunks, let's call those things like this, in the different part of the circuit. So basically, I will show you how it works. Also, I have also the example of that. And one big change right now is the C language API, because basically we know that a lot of the HP systems and HPC use cases are using the C language. So that's why we're adding this C API into the systems. And one thing which is also important for us is how you can run circuits accurately and directly on the hardware. So basically, as you can notice over here, this is for me extremely important, extremely useful thing, which is the quantum dynamic circuits, where you can use them for a utility scales use cases. So going back to those different points, I just want to just draw it through quite fast through those things. And as you can see, you can basically see the main focus right now will be on the connecting and orchestrating the system to give you the possibility to interconnect between the quantum CPU and GPU systems quite fast and quite easy during your code execution. Okay, I will not go with this details much deeper, because as you can see, there everything is on the roadmap. But where we are on the innovation roadmap, and as you can notice, right now we are in 2025 still, but actually we already proved that error correction decoder to demonstrate the real-time error correction is already up and running. So our recent research shows that we are able to demonstrate that kind of system already. And as you can notice over here, there's like a small green tick next to one of our new hardware systems, which is the Loon system. I will tell you a little bit more about the system, how it's designed, and how it, in my opinion, change the hardware design in IBM, and shows how you can use the C couplers inside the system for fully tolerant, fully error corrected system. So this is one of the hardware systems which are in the road for the quantum advantage. And as you can notice, we already incorporated the scaling with L couplers, long wave couplers, already in Flamingo. This is the chip which will be also available. It's already built and will be available soon, but right now we are using the Heron's systems and all of the systems in the cloud. Right now we are using the Herons, usually in US data center. Maybe I will just show you that because it can be interesting for you guys. So let me just switch to the browser for a second. How to close this part? I need to move it. Yeah, okay, now it's fine. Okie doke. So I will just hide the toolbar. Okay, so going back to the systems, and I want to show you the Marrakesh system. So basically, those are the statistics on the Marrakesh system. So as you can notice, we're still using the heavy hexagons architecture, but look at the numbers of jobs pending online for this system. This is live API calls to this system. And if we go back to the overall statistics for the system, so this is the number of circuits run. I will not even try to read this number, but you can notice that's quite a huge number. And here are the maps, map statistics on the countries who are actually using. And as you can see, the heaviest users are over in US and also here in Spain, as you can notice, and of course in Germany. Okay, let's go back to the presentations. I will just show, sometimes I will switch to this deck to show you some of the features. So going back to the presentation, as you can notice, probably, we will be introducing the systems which is called Nighthawk. This is the platform which will be still using so previously we used heavy hexagons, as I mentioned, on the Heron systems, but right now we will be jumping to the different architecture, so it will be like a square lattice. So thanks to this one, we will be able to support much more efficiently the circuits with the fewer gates required to information routing. And as a result, you can run quite much more complex systems on the same gate scale. Of course, I have the more details on the next part of our conversation. So, but for me, important, those are the two systems. It will be Starlink and BlueJay. And Starlink will be the system capable running of 100 million gates on 200 qubit devices. And actually, it will be shown in 2029, and then on 2033 we will have the BlueJay, the system, which will be even bigger. So as you can notice, 1 billion gates on 2000 qubit devices. Okay, I will just go a little bit to this quantum experience and the software algorithms. This is quite important for us because basically what we are looking for right now is demonstrating the accelerator streamlines for quantum advantage and also fault tolerant instructions for architecture, including the magic state and stuff like that. So I will show you a little bit more, of course, a little bit later, but those are the things on the innovation part, which actually those green things are already already embedded into the Qiskit part. Some of them are used as a functions. Some of them will be embedded directly into the Qiskit. So, showing the roadmap, I want to just stress one thing, that for over 6 years in a row, starting from 6 years now, every single tick, the green tick which I already showed you, were already met as a target. So basically, what I want to say, 2026 quantum advantage, 2029 full tolerant quantum system. So basically, this is where we are heading. Okay, as we started the conversation about the hardware, I just want to show you a little bit on the older stuff like Heron. You already are familiar with the Heron system, but actually what you can find right now on all of the systems, we are on the revision 3, and as you can notice, this is the it has the longest T1 time and also the lowest error rates when we are just using the system with the Heron 3. And one thing which I want to show you is also that the Heron is a kind of building block for our Flamingo system. So in Flamingo system, we use Herons and add the L couplers gates, connected those gates between different chips. So basically you can find those couplers, you can see those cables which we already introduced. And those cables can be used to connect chips up into 1 meter apart. So allowing the increased speed, flexibility, wiring inside the fridge components. So we change a lot of stuff inside the fridge just using those couplers. But probably you remember on the roadmap that we introduced the system which was called Nighthawk. I just want to show you how the system will look like. So this is the introduction of the Nighthawk of the system. This is like a square qubit topology. It has 120 qubits with 218 couplers. It has 42 more couplers than Heron. And thanks to this one, you can run we assume that it will be like a 30% plus more complex circuits than on Heron. And one thing which we are heading right now is to decrease the errors and also the assembling the time which will be used for the next systems. So just showing you how the system will look like. So we have something like tunable couplers, and our road for the full tolerant quantum system will be based on the quantum low density parity checks, where you can use 12, for example, 12 logical qubits into 144 data qubits as a gross along the another qubits. For the total, we will have around 288 qubits. So this code corrects error as a surface code and requires 10 times fewer qubits to do so. So basically what we are looking for universal computation, which can be done by adding additional stabilizer, communicating with magic state factories that will create and distill consume magic states to apply universal gates. And our team already made numerous contributions to the development of these magic state preparation protocols since 2024. And if you will check the latest papers about the explicit universal fault tolerant instructions set using adapters and the Magic Factory modules, you will notice that adapting of this bicycle architecture will enable operations on the universal quantum computing, and the last steps of the error correcting code will be induced inside the Sterling proof of concept, which will be deployed in 2028. How this system and how those tunable couplers will change the code of the length of the code. So here are some of the examples of the depth. This is the heavy hexagon lattice system, and you can see this is a depth 48. And on the square lattice system, we will have a depth 4. So basically, as you can notice, we can, this is like a toy example. It's just a playing with the depth of the circuit with the connections. But if we will just run some kind of Hamiltonian simulations, this is one of the examples which was done in 2024. You can see the decreasing of the depth of the overall circuits. Also, what we change and also what we introduced this year is possibility to scaling the hardware to 300 millimeter processing. So basically what we are having right now, we built a Nighthawk and the Loon using the 300 millimeters fab line in Albany Nanotech Center. And our devices expect the magnitude of increase complex compared to Heron. I will show you those comparisons because it is amazing. You can notice how the fabrication change from the line 200 millimeters fabrication line to 300 millimeters, and also how it demonstrates, let's say, increase the speed per waveform and how it will be used inside our chips. So a little bit about the advantage. So 2026, next year, what we are planning to do, we are planning to achieve something like a quantum advantage. So quantum advantage in our definition, because probably you can notice that there will be a lot of different definitions. So in our point of view is this ability to execute information tasks on the quantum hardware, which has the correct and can be rigorously validated, and also separation where the quantum computer will show the faster results than the classical system. So this is where we are heading, and how we want to achieve it is quite impressive, because first of all, we built the two parallel paths. First one is those are the empirical tests of quantum usefulness, which, as you can notice, are already shown on those papers. And another point is how to prove the advantage. And of course, we rely quite heavily on our network, which we built through those years of the constant development of the systems and also the relations and our partners. And we introduced something which is called Advantage Tracker, which is available in the GitHub, actually. And let me just go there for a second. Yeah, there is it. So we have right now on this one. So the main point is that everyone in the world can go through the three different tracks. So first one is observable estimations. Second one is variation problems, and third one is the classical variable problems. The main idea of this quantum advantage tracker is giving the opportunity to the wider community to check if the runtime on the quantum system will be faster than on the classical system. So basically, it's not like we will say, okay, right now we achieve advantage. No, it will be like I said at the beginning of the advantage point of view. It will be proof. It will be verifiable. Let's say like I'm not sure if this word even exists, but you know what I mean. So there must be a proof. There must be a paper. There must be also, as you can notice, you can have an access to the circuit. So you can run a test of the proposed algorithm and the proposed problem, which can show the possible advantage. Okay, and actually, as I mentioned, everyone can participate. That everyone can send their own idea, their own circuits, and also if you have the willingness to help us, if you will have the willingness to check the algorithms, you can also participate in this contest. It's not the contest; it's just a one way to show the possible advantage. So basically, everyone can, because it's the project is on GitHub. So basically, everyone can have an access to it, and everyone can run their own tests. Okay, let's talk a little bit about 2029, where we want to and how we want to achieve this breakthrough. First of all, we want to build a system which will have the hundreds of qubits capable of running of hundreds of millions of gates, and also more than 100 million of operations with a broad resistance to failures. So this is the system which we want to show. So first one is, of course, the quantum error correction techniques, multiply techniques, different techniques. Some of them techniques will be the code correction. Sometimes will be the correcting of the physical qubits. Some techniques will be important to reach desired scale on their own. And next one is, of course, the fault tolerance. So computing capabilities and adding the possibility to apply the quantum error correcting code on the computation scale. So to show and prove efficiency and possible advantage around this space. So how we want to achieve it? Again, we need the hardware And I just want to show you how the system will look like, where we will be building and using the Loon system. So have you can see here you can see how the Loon is built. So it has additional 6 layers of connections, and the qubit connections between the nearest neighbors indicated by the colored lines in the blue and the pink. And it's in this view, you can appreciate the significant uptick of complexity with multiply high-quality layers enabling 336 couplers, and it's about 2 times more than in Heron. Starting with the basic, Loons will allow us to implement the graph of error correction code. So you can map the donut required to your QLDPC code into the qubits of inside the Loon system. How the system will look like? So this is the system architecture. As you can notice, it's quite heavily packed. And first of all, again, 356 couplers, and processor will it will require new features. So it will be 6-way connections, 6-way coupling, additional layers of high quality routing, long coherence times, long couplers, resetting qubits without disrupting the neighbors, and also for all of the let's say for all of the components, the tool will show how you can connect those systems and also how you can use the system comparing to the previous versions. So I will show you how the previous version will look like. It looks like. So this is a Heron, and this is the Loon system. So basically, you can see the huge difference inside the architecture. The side-by-side comparisons shows the current Heron, and now you can notice that how, first of all, complex, and how the connectivity, in our opinion, will improve the using of the systems, because in your code you will be able to use 10 times less physical qubits in the surface code. So this is we already saw, but in our opinion and our approach, it will be like creating, let's say, next steps up to the Starlink in 2028 with this magic state factory, where we will use those new techniques and technologies we embedded into gross code block, so this 6-degree couplers. Then in 2076, we want to have a possibility to gross code plus the logical processing unit, the so-called LPU. And we will just use those long C couplers and this LPU to improve the, let's say, to use as a logical memory. Next steps, 2027. This is the two models connected with the L couplers. So basically you can see this additional connection. And next we are connecting the magic state factory to allow universal computation. And this will be like a main foundation for the Starlink system. And here are the micro images of the Heron and Loon system already let's say incorporated, engraved into the silicon system. So one thing which I want to show you, and I will encourage you, it will be good. Maybe I will be able even to. Do I see somewhere the chat? Yes, here is the chat. So I will just send it to the chat. And what I will encourage you to go to ibm.com to the Quantum, and you can see the information about the Nighthawk system. You can see the information how it will be built. And then you have the new features around the Qiskit, so C++, which are introduced in the Qiskit 2.2.3. And here are the informations on the hardware. I will totally encourage you to go there. You can see what kind of system data centers we have, what kind of processors we have, and how the innovation looks like. So this is the silicon plate with the newest chips which we introduced in our system. And also you can see how those couplers, so this is the connection between this is Flamingo system, so you can see how those couplers are connected together, and also how we want to achieve this for scalability for the infrastructure. So you can go here, you can explore how the system, how the cryostat looks like. You can play a little bit with the system. You can see how it looks like. It's kind of cool also to show how the system works, how the system looks like. So here are the informations about the processors, everything which, if you are interested with the processors, systems and data centers. So as you can notice, we introduced already the IBM Quantum System 2, which is over here. So this is like a system where it's already prepared for HPC data centers, and actually this first system was deployed in the Basque Country this month. It's kind of interesting. So if you are looking for a quantum roadmap, you will also have the quantum roadmap, but I will totally encourage you to go to this blog part where you can find all of the freshest informations about, for example, the scaling the beyond the roadmap, so something which we are interested. So I will just jump it for a second. I don't want to just disturb the presentations, but want to show you something which we are heading, and this is something like a quantum network where you have the connections between the chambers, but also sending the informations with the microwave optical transductions to the quantum sensors, and creating something like quantum computing internet. Kind of interesting area, but it's, as you can notice, it's a little bit beyond the roadmap of the quantum systems. So again, I will totally encourage you to go to this page and check the system. Let's say the freshest news, the blog messages, and I'm just taking the freshest informations directly from there. Okay, and I mentioned about the Starlink. I mentioned about the first large fault-tolerant quantum computer, and everyone said, it's impossible. It will not be never delivered, something like that. So again, in my opinion, 2029 will be the year, and this is what the system will look like. So in 2029, we are about to create the new quantum data center in Poughkeepsie, and we expect it to perform 20,000 times more operations than today's quantum computers available in the cloud. The quantum computers state inside the Starlink will require memory which will be around 1 quindecillion, so 10 to power 48. It will be the most powerful quantum computer. This is the number of the most powerful quantum computers, and hopefully with Starlink users will be able to fully explore complexity of the quantum states, and actually in our opinion, it will be reached beyond the limit properties of the current quantum computers. So a large, fully tolerant quantum computer with hundreds of thousands of logical qubits could run of the hundreds of millions or to billions of operations, which could accelerate time and cost efficiency. And for example, in the drug development, material discovery, chemistry, optimizations. And Starlink, in our calculations, will be capable to deliver 100 million quantum operations using 200 logical qubits. This one will be a foundation for IBM Blue Jay, which be capable. This is what also what I showed you when I was when we were talk about when we talk about the roadmap. So the BlueJay will be capable to execute 1 billion quantum operations on over 2,000 logical qubits. And this is, as you can see here, we are already starting the assembly of that kind of system. So main steps, I will just go for a second here. So the main steps to reach inside the road, let's say to which I showed you on the roadmap, it will be like a IBM Quantum Loon processor 2025 still will be. This is like one of the steps. Next is a Kookaburra 2026. Kuka 2 expected 2027, which will be the entanglement of the Kookaburras using L couplers. So I will just jump for a second here. So this is the roadmap how we want to achieve this system in 2029 incorporated inside the inside our data center in Poughkeepsie. Okay, but what is now? What do we have now? What we are doing now in IBM? What you can also play with. So first of all, IBM Quantum Platform changed. Maybe you noticed, maybe not, but even today when I was trying to log into the system, Quantum Platform looks much different than the previous ones. So basically, as you can notice, the quantum system is part of IBM Cloud. So the access, account settings, and everything IAM is related with your IBM ID, where you can log into the IBM Cloud. Inside the IBM Cloud, you need to create an instance for yourself. Then you can use the free 10 minutes of the plan, which is kind of cool because you can run your own experiments without paying any money. This is like a free of charge. And then you can see the quantum computing resources which are available. And as you noticed, we have right now 2 different data centers where we just deploy the system. So first data center is located in US East. This is like, again, IBM Cloud. You can see here we have 6 Herons over here. Half of the, let's say we have even the Heron revision 1, we have the Heron revision 2 and 3, and we have the deployed system in the Frankfurt. I will jump it. And then in Frankfurt, we have two Eagle processors and 1 Heron processor. And let's go back to the Washington. And you can see this guy, the Marrakesh. This is the busiest processor ever. Everyone is using that because it has the short execution time, and you can run up to the 200 CLOPS, so it's called circuits layer operation per second. And again, as you can see, you always can play with the system again, like in the old platform. But what's changed now, it's also we adding the Qiskit functions catalog. So basically, you have those application functions which are provided by our network members, and those are ready to be used, the functions. Let's go for the chemistry, for example. So cutting edge classical algorithms, Solos approximate molecular ground states using the, and so on, so on. So basically you have the possibility to play with those functions like in the regular Python functions. So basically you can use them inside your circuits. And of course, one thing which is important, if you are looking for documentation, tutorials, API references, you have everything over here. But one thing which not disappeared, which I like the most, of course, for education purposes, is the graphical user interface for to create a code. Still, we have all of those features like just grabbing the gates, dropping the gates. You can see the state probabilities. You can see the state vectors. You have this code directly get generated by the system using the quantum assembler, but also the Qiskit. In the next releases, you will have also C++ as well. One thing which changed, and I think is worth to mention, you can run a circuit only on real quantum systems. So right now we are not providing any simulators, but still you can use the simulators on your system if you will deploy the Qiskit on your own laptop or your own data center. You can still use the simulators on your on-prem deployments. Okay. And for a Qiskit, what changed? So we have 10 minutes, as I noticed. I promised to Pavel that we will finish up to the 7 p.m. So I think, Pavel, probably.
If it's a few minutes later, then it's still okay. But
Okay,
anyway,
okay. So I
we
will
can
try.
continue. We can continue
Yeah, okay.
later on.
I will try to be fast, but I just want to show you two couple of important informations. So basically, Qiskit, you know the Qiskit, how it works, but there are some kind of additions. So those are the orchestrations which we are right now introducing. So first one is the Slurm plugin for HPC. And also we have this bench press. So the place where you can run the benchmarks of your hardware. And of course the quantum hardware plugin where you can connect different add-ons and different hardware systems across the different vendors. So I want just show you one thing maybe, which maybe gives you some kind of yeah. I will go with this quantum-centric supercomputing. This is our approach. This is our goal to incorporate quantum system with the supercomputing. How we want to achieve that? This is one of the ideas. So first of all, we want to do the foundations for algorithms where you can use two approaches. So first one, it's a seamless way to integrate quantum to the scientific computing environments. Second is developing of the new capabilities and exploiting the quantum-centric supercomputing architecture. So basically, what we are using a Slurm, and you can build a workflow to do some kind of interesting stuff which you want to deliver. And here is the one of the examples. Maybe I will just use this one. So this is one of the examples of the workload management provider, which is used by one of our members. So we are running Qiskit primitives as a part of the bigger algorithm workflow, and we are demonstrating how we are picked the SQD algorithm, which was shown by our partner, and mapping a circuit optimizations, execution, and post-processing as a task of the workflow, and execute those parts in the kind of native HPC fashion and the HPC way. So this demonstration shows how you can embed the workflow inside heterogeneous system like quantum-centric supercomputing environment. So basically, as you can notice here, we have you have here the vQPU, you have here the API to the system, but you have the classical job queue and the quantum circuits. And one thing which is also important, and I think it's worth to mention, I am not sure if I have the, yeah, I have this part, will be the introducing new thing inside the circuit to give you some kind of, this is the flavor. I will not take more of the time for now, but I just want to show you something which I think you can be interested with. So this one is like a new thing which is called Samplomatic. So Samplomatic is the way how you can cut the parts of the circuit, and you can actually add some different behaviors across the circuit. So boxes, as you can notice, supports definitions of the regions, how the symptomatic will behave with the different annotations and the different operations inside your circuit. So basically, what you are seeing here, you can use you can define additional primitive interface, which is called the executor. This guy over here, and it's right now it's now supported on IBM Quantum computers, but actually it allows you to run a circuit templates on the corresponding samples. So you are dividing the circuits and you are applying different templates. It's something new, something which I think will give you the possibility to execute the the circuits in the way that you are not just running a one circuit and just waiting for it. No, you can just divide the circuit to the smaller chunks and then realize a different approaches like noise injection, like poly twirling, and so on, so on. So this is how the executor and samplomatic will be embedded into this part of the optimization of the circuit. So what will happen next releases? This is 2.2 October 2025. You can see here. So expanding the CFFI, so transpiler functions, standalone transpiler pass, and so on. And in the November 2025, it will be also, we are just expecting to have this release quite soon. So one thing which I want to just show you one last minute is, first of all, how our ecosystem looks like. We have right now 300 plus members, 170 academia, 65 commercial partners, and this is like a user community ecosystem, which is huge. And since a couple of years, we work on the different plans and different possibilities how to use IBM ecosystem. And we have right now, as you can notice, we have 4 different ways to work with us. First one is the premium access. Of course, this is the plan where you will obtain the most. Then you have a flex plan. I'm jumping. Yeah, you have a flex plan, and basically you can somehow align the plan to your problems with the funds which you have, and of course, here is the open plan, so pay as you go. So you can use open, free, then you can go pay as you go. But also, one thing which is, in my opinion, quite interesting for many of the education and not only education partners is creating an on-prem plan, and basically we already deployed the quantum computer systems. So we built 60 devices, less than 100 qubits, 25 devices, more than 100 qubits. And like I mentioned, we have 2 data centers in IBM Cloud, but also you can see here, we deployed those systems across the world, and we are working with the partners to so for one I want to just this one. One system which was deployed quite long time ago. Yeah, this is this system, and in this guy we have the Eagle processor, and we are up to the upgrading the system to the recent Heron version. So basically, the client already will have the freshest version of the system. So what's happened in the let's say algorithms and how it works. I showed you what is inside IBM and what is inside our development, how we look like on the system. But I just want to also show you one thing, which is, in my opinion, quite important. Uh, what our partners are doing. So actually, right now they build around 95 plus prototypes and built by themselves with the industry applications. You can see a couple of scientific papers from Bernie, Cleveland Clinics, Moderna, Eon, latest HSBC, where they are working quite extensively how to create an advantage, how to use the quantum systems efficiently into the industry application. So it's not only the research phase, but also this is the place where we want to use those systems into the real use cases, real world scenarios. So guys, I just want to finish this meeting with one sentence. So let's create the future quantum computing together. This is not just a sentence, it's just the way how the quantum scientists, quantum nerds, quantum educators can give their own brick to this quantum world. So, first of all, get started with the IBM Quantum platform. Go there, scan QR code, begin experiments, begin to learn, and we are inviting you guys to check the recent news and also to find out and help to judge if we achieve the advantage yet or no. So with this sentence, I just want to thank you very much for your attention and for the hour which we spent today. Pavel, as we just discussed, if there will be like a willingness, we can continue and go
Yes.
deeper and deeper into the Qiskit part of the recent announcements. Okay,
Okay.
so
Great.
with this
Great,
one, I
Piotr.
will stop sharing and let's do the housekeeping.
Okay. Thank you very much, Piotr. Thanks. Yes, indeed, I asked Piotr to finish before 7 p.m. because I will have to leave soon. So there was a question about recording. Yes, it is recorded, so we hope to upload the video later to our YouTube channel. It should be available. And I hope to have another webinar, another meetup with Piotr in the future. Um, Unfortunately, we do not have time for questions now because I will need to leave. So, but anyway, I
But
have an
Pavel, I
idea.
just, as you notice, I
Yes,
just dropped my email. If
yes,
there will be any willingness
yes,
to connect to discuss, join me, send me an
yes,
question. Also, if you like, I'm on the LinkedIn. Ping me on LinkedIn. We can have a conversation. We can
yes,
have a meeting.
yes.
I
And
can guide
actually,
you through
yes.
this corporate world.
Actually, I have one more idea because the fact that I need to leave doesn't mean that the other people have to leave. So maybe I'll now stop recording. And Piotr, if it's fine for you, if you still have time, perhaps you can just stay here on the Zoom with other folks for some time if there are any questions. But I will just need to leave, so I will just leave you with the participants. But anyway, as we discussed, I'll be very happy to host you once again in 2026, so we can later discuss when to organize the next lecture.
Yeah, no problem. Of course. So, Pavel, thank you very much again for the invitation,
Thanks.
and
Thank you.
happy to be in 2026, and also probably we will meet on in many hackathons and
Yes.
organized let's
Yeah.
say actions through the quantum community in Poland. Thank you very much again for
Thank
the
you.
invitation.
Thanks. I will now stop recording.